Let's look at one more example using Newton's method. This time I want to use it to approximate a point of intersection between two functions. I have y equals x cubed and y equals x squared plus 1. I'm going to approximate the point of intersection between those two functions using 3 steps of Newton's method. So here I'm really trying to solve the equation x cubed is equal to x squared plus 1 to find out where these two functions intersect. Now, Newton's method is not directly going to give us an approximation for a point of intersection, but we can do a clever bit of rewriting here by setting this function equal to 0 and saying, okay, x cubed minus x squared minus 1 is equal to 0. This is now the equation that I'd like to solve, and this is going to give me the same x value. And now I've written it in a way that Newton's method will work here because I'm trying to find an x-intercept. I'm trying to find where this function crosses the x-axis. So, okay, let's set up our function here. So this is our f of x, and maybe we'll go and find f prime of x as well. That would be 3x squared minus 2x. So if I wanted to come up with the formula for x sub n plus 1, I would be taking x minus f of x. So f of x is x cubed minus x squared minus 1 divided by f prime of x, that is 3x squared minus 2x. Again, this guy right here just coming from the definition of Newton's method. Remember that it's coming from x sub n plus 1 equals x sub n minus f of x sub n divided by f prime of x sub n, just in case we forgot. So this is what I'm going to use to find my subsequent points. So now all I need to do is take the x naught that I have and plug it in, and we'll just start going. But, it didn't give me an x naught this time. If you're not given an x naught, you may need to come up with one on your own. So I'm going to look at the graph of these two functions, x cubed and x squared plus 1. So here I have the red function as x cubed, the blue function is x squared plus 1. I'm looking for this point of intersection between the two right there. So I'm looking at that. That looks like it's between 1 and 2. To me, that looks like it's a little bit closer to 1. I'm going to pick my initial starting point to be x equals 1 then. We could probably get a little bit closer if you wanted to say 1.5 or 1.25 or something like that, but I'm just going to stick to x equals 1 here. So I'm going to use x naught equal to 1. So if I want to find x1, this is equal to 1 minus 1 to the third minus 1 squared minus 1 divided by 3 times 1 squared minus 2 times 1. And so what I end up with here, 1 minus in my numerator, I end up with negative 1. In my denominator, I end up with a positive 1. Here, 1 minus, or rather plus 1, is equal to 2. So this is my x sub 2 here. So now I'm going to repeat this process. This is my x sub 1. I want to repeat this process now to go and find x sub 2. So this will be 2 minus 2 to the third minus 2 squared minus 1 divided by 3 times 2 squared minus 2 times 2. So I have 2 minus. In my numerator here, I end up with 3. My denominator, I end up with 8. I have 2 minus 3 over 8 right here. So 2 minus 3/8 will end up being 13 over 8. Or if you wanted to give a decimal approximation, we could give that as 1.625. This is my x2. If I wanted to find x3, I would take this number and plug it in once more. So let's do one more step here. If I wanted to find x sub 3, I would take 1.625 minus 1.625 raised to the third power minus 1.625 squared minus 1 divided by 3 times 1.625 squared minus 2 times 1.625. So let's see here. I'm going to have to do a bit of rounding, and that's okay. In my numerator, I should end up with 0.6504. In my denominator, I have 4.6719. And here, when I take these two and subtract them, 1.625 minus 0.6504 over 4.6719. Here I end up with 1.4858 if I round to 4 decimal places, and this would be my x3. And obviously I could continue down the road here. I could find x3, I could find x4, and so on. But this is the idea here, is that we set these two functions equal to each other. So we took our functions, set them equal to each other, and then set that equation equal to 0 and forced it to allow us to use Newton's method to approximate to 0, which would be the same as the point of intersection between these two functions. So our last approximation, 1.4858, let's actually see what Desmos gives us here. We have 1.466, so that's pretty close. Again, within 2 decimal places, it looks like. That is fairly accurate, I would say. So this is a really, really neat little application of the derivative. I think it's a cool little trick. It's not anything groundbreaking. We're not going to use it a whole lot. There's only a couple of problems for the homework in this section, but I think it's just kind of a neat little trick that we can do. Whoops. One last thing that I'd like to talk about here is how Newton's method can fail. So there's a couple different ways it can fail, and it's kind of interesting just to look at what could happen here. If I look at this example here, so notice here is x naught. So watch what happens. I'm going to take x naught, I create the tangent line right here, and then I say, okay, here is my x-intercept. This is going to be my x1. Oops, that's going to be my x1. So then I create the tangent line there, and I find the x-intercept, and I say, okay, where's my x-intercept? It is right here. That's going to be my x2. And then I say, okay, let's build the tangent line, and here's my tangent line. Well, where is the x-intercept of that tangent? It's right here. That's my x3. And then I say, okay, we'll build the tangent line right there. And do you see what's happening? I'm just going back and forth and back and forth. We start with x naught, and then we go to x1, and then x2, x3, x4, x5. We're going to repeat forever and ever and ever. So we'll have some special cases like this where Newton's method actually isn't going to get us anywhere closer to that point of intersection, right? This is the point that I want to find. I want to find that point of intersection, which this one's pretty easy to look at and say, well, yeah, it's just 0. But there may be instances in which we kind of hop back and forth between the same two x values. We just sort of oscillate between those two x values over and over and over and over again. So Newton's method doesn't actually get you anywhere. Just kind of the wheels are spinning, but you're not actually moving. So that's kind of one instance. Another instance here, this one is not quite as obvious. You can converge, so you might still converge to that point of intersection. Again, this is our point of intersection, but we might converge very slowly here. Usually if we pick a close enough x value, you will get to that point of intersection relatively quickly. We saw we got within 2 decimal places in 3 iterations of Newton's method, which is pretty astounding here. But here in this case, 0, look at our... We're obviously heading to 0 here. That's where our x-intercept is. So, but look at our x naught. If we start at 0.15, then we end up with 0.07 if I round, then 0.34. We're converging to 0, but we're converging to 0 very, very slowly. So this isn't necessarily a huge problem for us, but this just means we're going to have to do Newton's method a lot of times before we get anywhere close to finding that root. The last method, and this is one of my favorites here, is when Newton's method fails because we actually get farther away from our x-intercept. So again, this is the point we're trying to find. We're trying to find that as our x0. Here, if I pick if I pick x0 to be 1.1, I say, okay, there's x1. Let's build the tangent line right here. And okay, there's my tangent line. And I say, okay, let's find the x-intercept. It's right here. And I say, okay, let's build the tangent line for that x-intercept. Well, it's going to be right here. Look at what just happened. x0 right here is 1.1. x1 is negative 1.4. Now, it's not uncommon for us to jump onto either side of the x-intercept, of the root. We actually saw that in the last example that we looked at, but we actually got farther away. Negative 1.4 is farther away than 1.1. And then in the next jump, we actually got farther away still. So you can have instances like that where Newton's method diverges actually to infinity. It's actually kind of a really interesting point of failure of Newton's method, is because it sort of just blows up, like you just get actually farther away from your zero rather than closer to it. So you may see these from time to time. I don't think there are any like that in the homework, but I think it's a really interesting point of failure for Newton's method, just to see it either oscillate back and forth or diverge to infinity. I think is a really, really cool instance, or a very cool scenario.